Okay, so the DMUs, you have when you're doing a multiplier model, it is subject to the constraints are the DMUs. So for each DMU, you have a constraint. For each DMU, you have a constraint. But when you're doing the envelopment model, the constraints are the variables. So you have input 1 constraint, input 2 constraint, output 1 constraint, output 2 constraint. So the constraints are for the variables. But when you are doing the multiplier model, the constraints are for the DMUs. So in order to really understand this multiplier, envelopment, linearizations, and all of that, what I'm going to do is to take this basic example. Please follow me as I walk you through this basic example so that you can, my advice is that if possible, you can just write the names of the DMs. Sorry, you can just write the data, okay? Just the input and output. As for the output, you know that it's been normalized to 1. So there is no issue there, okay? What is key is the input and output here. And in the input, we have 2 inputs, which means that we are dealing with an input orientation since the output is normalized to 1. The DMUs, I've given them kind of 2 different names, and you will understand why in the course of time. The first DMU is A, and it is a DMU 1. The last is E, and it's DMU 5. Your job and my job to guide you in this process is to formulate the input-oriented multiplier model, fractional programming model for DMU E. Now remember, this is an input-oriented, so it's not going to be exactly like the one we did before, but it's going to be the opposite of it. And then we are going to formulate the same VRS linear programming model for the multiplier. That means you are going to linearize the fractional programming into a linear program. Then we will convert it into the envelopment version. We will draw these observed data points. We will generate the frontier, the radial lines. We will do all of this in R and in normal graphic. R is going to do the computations, the drawings, and everything for us. And then we'll interpret the scores. This is an input-oriented model, so you can extend it to an output-oriented or even non-oriented or even both input and output-oriented case. All right. In the course of these lectures, I'll be changing some of them. So let's get down to understand the formulation. Okay. Now, so let's formulate. The first thing we're going to do is to formulate the input-oriented multiplier model for this. Now, let me just remind you, all these while we've been using the output-oriented. So let me just remind you what an input-oriented graph looks like. This is what it looks like. So in an input orientation, you are minimizing the ratio, which is the weighted input over the weighted output. Please watch. It is not the same as the output oriented, where the output is rather at the top and the input is below. This time is an input orientation. It's an input orientation. So the output is below, the input is above, and you are minimizing the ratio. You are minimizing the ratio, subject to the constraint that the same ratio, with the numerator being the input weighted input, the denominator being the weighted output, and that is greater or equal to 1. If you can remember the output orientation, it was less or equal to 1. The number of frames are J from 1 to N. And then the weights are V's for the input and W and U's for the output. Remember, the inputs are from I from 1 to M. That's what you see at the top. I from 1 to M. And the outputs are from their R from 1 to S. Okay. But the key point I want you to notice that you are minimizing. This is an input oriented. You are minimizing. Can you write down the formulation for me using this data set? Can you write down the formulation using the data set? So I've looked at most of your works, and I'm quite impressed with some of you, what you are doing with the multiplier formulation. So let's show that on the screen. Okay. So you minimize the efficiency of this particular DMUE subject, and the efficiency is that your goal is to find the weights, which are U1, V1, V2. And I think one of you was wrong. I don't know which one. Okay, I think I am even slightly wrong here. Let me make some few changes. Okay. So you minimize, and the DMUE or the DMU5, the inputs are 7.5 multiplied by the weight, which is V1, plus 3.3 multiplied by the weight, which is V2. Okay. So that one is the ratio. And then subject to the constraint, you do that same thing for each other firm. Okay, for each other firm. So the first center, the constraint will be 3 V1 plus 5 V2 divided by the weighted output. And that should be greater than or equal to 1. Now, if you can remember the output orientation, it was less than or equal to 1. You do the same thing for the center 2, 3, center 4, okay, and then, of course, center 5. Okay. Now, you don't forget your non-negativity constraint. The non-negativity constraints are U1, V1, V2 greater or equal to 0. And you have to understand that the DMUs are 1 all the way to 5. So this is how you formulate the fractional programming problem. Now, how do you convert this into a linear programming problem? Multiplier. How do you do that? Okay. I want you to do this and also show me that second one. So this is a multiplier model, okay, for the formulated model. Now, if you want to send it to a linear version, you have to maximize this one here. You maximize it. And what do you maximize? Okay, so here you're going to maximize the variable that you are dealing with its, we are dealing with input orientation. So because you are dealing with the input orientation, you are going to maximize not the input, but you're going to maximize the output. And then you set that input to 1. Okay. You are going to maximize the output, then you set the input to 1. That is the one whose orientation we have chosen. So what it means is that you're going to maximize the value. I want to call it like Z. Okay, let me just write it here. I want to call it like Z. So you are going to maximize this Z, and Z is actually the one you want. Okay. You're going to maximize this. And then you set the input 7.5 V1 plus 3 V2. You set this one to 1. And then the rest, you can apply your cross multiplication. Okay. You can apply a cross multiplication and then move the one U1, which will be on the right-hand side, to the left-hand side, which will be minus. But it's better to move this one rather to the right-hand side, and then it becomes. So in short, what you do is that I want to make the input minus. So what you do is that you cross multiply. The 1u1 will come to the right-hand side. Okay. And then that you swap, and then that 1u1 comes to the left-hand side, and then the 3v1 goes to the right-hand side, which means that the sign is going to change. Okay. So you can move all of the 3v1 to the 3v1 plus 5v2. You can move it to the right-hand side, okay, which makes it minus. And then you can now change the sign. Okay. I mean, at this stage, you can do anything you like, as long as you know that anytime you multiply through by a negative number, the sign will change from greater than to less than. So when you do all of that, in fact, the main one is what I've just written here. Okay. The rest is just following the gimmicks. So when you do all of that, this is what you're going to have. Okay. So you maximize this z, and then for center one, you're going to have this, as you can see. This is just when you do the first cross multiplication. But the input, since it's the one that we are dealing with, remember, this is an input orientation, and this is a multiplier model. Okay. And you will have all of the variables this way. Now, if you want to convert this one properly, and again, it's still in the multiplier form. It hasn't changed the multiplier form. Okay. It's still multiplier. Okay. You can now change the sign, as you can see I've done here, change the sign to less than or greater than with a 0 on the right-hand side. And then the input will now be minus. If you do a proper change of subject, you will get something like what I've just shown here. And as you can see, the weighted sum of the input is equal to 1. So this is still the multiplier model. How do you now convert this multiplier model to the envelopment model? Now, this is where it is interesting here. This is the one that, David, you were really asking about. What you do here is, remember, this is an input. And I told you that with the envelopment model, you are modeling along the lines of the constraint along the lines of the input, but you do it for each firm. So this is going to be the output. Okay. So the first input are these very numbers. So you're going to do lambda, 3 lambda 1 for the first one. Okay. Going to do 3 lambda 1 for the first one, 3 lambda 2 for the second one, 3 lambda 3, 5 lambda 3, 8 lambda 4, 7.5 lambda 5. And that is going to be for the first input constraint. And of course, when you have that, it will be less than or equal to the input of the firm you are evaluating. And what is that? The firm you are evaluating is DMU5. So the input of the firm you are evaluating, which is DMU5, okay, that is going to be, so this is going to be less than or equal to 7.5. Then you attach the theta to it. Then you do the same thing for this second constraint. And this second constraint is also for the input. So you do it for that one, and then you do less than or equal to 3 theta. And then you do for the output constraint. Okay, they are all 1, 1, 1, 1. And that one will be greater than or equal to 1, which is for the DMU5. And then you attach your non-negativity constraint. The non-negativity constraint will be for the lambdas. Now, the non-negativity will be for the, so that one is going to be lambda 1, comma, okay, lambda 2, comma, all the way up to lambda 5, okay, greater or equal to 0. This is a non-negative constraint. If you have a VRS constraint in addition, variable returns to scale, then these lambdas are added together and they are equated to 1. Okay. The lambdas are added together and equated to 1. Let me show you how this becomes eventually. So the most important thing is to try and understand the formulation, because this is what you see in journal articles. This is what you see in journal papers. So this becomes the formulation for DMUE. That's the first constraint, the second constraint, the third constraint, and then eventually you will have the output constraint. And, you know, of course, this one we use the 1. You can use the 1 or the A or the B. Okay, you just have to decide. And then you have the VRS constraint. If you have CRS constraints, you don't need the VRS constraint. And then the final one will be the non-negativity constraint. The fact that we have a VRS constraint means that theta is made free, which means that theta can be exhibiting itself along the lines of increasing returns, decreasing returns, or constant returns. So theta has that freedom to operate in that regard. Master these formulations. Master them. Master them. In your thesis, you are going to create a hypothetical data set. You're going to draw the data set. You're going to show the frontier. You're going to formulate the DEA model. And you're going to show all of this. You have to. You have to get enjoyably used to doing this, because that's the only way that you can know that you've done a great thing. Okay. So that is it. Now, how do you explain the content of the formulation? Okay, this formulation that you see, how do you explain it? Okay, how do you explain it? So, in short, the linear programming wants to find an efficiency score for this DMU, and this efficiency score is theta star. It does that by minimizing the factor, which is theta, and that is a decision variable. Remember, the lambda is also a decision variable in the objective function. The theta happens to be both the decision variable and the objective function, but the lambda is a decision variable. Once you seek that efficiency score by minimizing that theta, it is subject to the constraint that the weighted sum of the inputs x1 or x2 of all firms, including the one you are assessing, okay, must be less than or equal to the input of the firm that you are assessing, or the targeted firm. And you do the same thing for the output as well. So at this stage, let's talk about the lambda. What is the lambda? What does it mean? What does it signify? What does it show? Okay. Lambda is an intensity factor, is a multiplier, is a weight. Okay. We call it a coefficient. If you check the variables very carefully, you see that, you know, the lambdas are attached to each input and output constraints, okay, for the firm. Okay, for the firm. So each firm will have a lambda. Okay, so firm A will have lambda, 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 firm B will have lambda. Okay. What is it? It is the importance assigned. And you got to determine this lambda during the optimization process. Okay. They are called the weights. And the weight of the peers for each firm. So if a particular firm, let's say that this DMU5, it does not put a lot of weight in DMU-A in identifying its performance. DMU5 or DMU-E here doesn't see DMU-A or 1 as a peer enough to help it to become efficient. It will not give it a positive lambda. It will give it a 0 lambda. So the lambda for that one will be 0, which means that whatever value that is here, it will be 3 times 0. So if the firm sees another firm as a peer, then it will give it a non-zero lambda. Okay. So those firms that have got non-zero lambdas, okay, those firms that have got positive lambda, because we know that the lambda is 0 or positive. But if it is not 0 but it's positive, then those ones are seen as peers or role models for the firm under evaluation. Okay. So it's important to recognize. Our next thing to do is to draw the whole table. Any question first before we move on? So now let's try to draw the data set. Okay, we plot that data set. You've seen it before. If you haven't, please do this. If you are actually doing this in your thesis, you have to generate the scatter plot yourself. Okay. So you highlight the data set and then you generate the entire scatter plot yourself. So please get used to doing that. And when you are generating the scatter plot, you don't have to highlight the headings. Say the headings are DMU or X1 or X2. No, you are just scatter plotting the numbers. So it's the numbers you are highlighted. Then you go to your Excel tab, you see something like draw. I think I've gone through this in one of the other videos. Okay, so you scatter plot and then you get this beautiful thing. And you can use different versions of the scatter plots to show the numbers or not. I wanted to show the numbers, that's why. So this is for DMU A, this is for DMU B, that's for DMU C, that's for DMU D, and then finally DMU E. So these are the DMs. Now what the DEA does is using the principle of monotonicity and convexity. It will now take the extreme values and then linearly combine them. Okay, it will linearly combine them. So after indicating this, you show the line. This is the first linear combination of A and B, the next linear combination of B and C, the next linear combination of C and D. After that, DEA will try to estimate the efficiency of everybody through a radial line. Okay. And so you can see that you have the radial line, and this radial line is from the origin to the firm. All of them are from the origin to the firm, from the origin to the firm, from the origin to the firm. But in the process of connecting them from the origin to the firm, they will cut the frontier, the boundary of the production technology set somewhere. Okay. And on the basis of where it cuts, you look at the gap, the difference between where the firm is and where it cuts the frontier. That difference is the inefficiency difference. But if there is no difference, that means that the firm is on the frontier. We know this already. Okay. Now, you have understood how this is done, but we have to estimate this using softwares. Okay. But I'll come back to that software thing. I just want you to know that the way you estimate the efficiency frontier is distance to the, and I'm talking about technical efficiency here. Okay. Technical efficiency, Farrell, even though sometimes Farrell will even consider weakly efficient firms. So note the definition of the efficiency. It's very important. If you are first time, the definition of the efficiency of any firm is given by distance, okay, from the origin to the firm divided by distance from the origin to the frontier. Okay, I want you to get that very, very well. So distance from the origin to the firm. So suppose I want to examine this firm, which is E, distance from the origin to that firm, that's the distance. So after getting that number, I have to read it downward. Okay, I have to read it downward. So where it hits the frontier, you read the value downward, and that is 7.5. Okay, so you note that value here. Then, oh, look at, sorry, I've made a mistake. It's supposed to be distance from the origin to the frontier. Okay, so let me make that clear before we move on. Let me make that clear. Okay. Let me just wipe off this. It's distance from the origin to the frontier first. Keep to that definition. To frontier first. Okay, and then you do distance from the origin to the firm. Okay, so from the origin to the frontier, That is this. And that gives you a value. When you trace it down, you get a value of 5. And then distance from that same origin to where the firm is. And when you trace that one down, that gives you 7.5. So you now have this 5 divided by this 7.5. And when you do that 5 divided by 7.5, that will give you the technical efficiency score of DMUE. Now, if you look at the rest, because you are on the frontier, okay, distance to the frontier divided by that same distance to the firm, you get it. When you trace it down, you get the same 3 divided by 3. And when you do the same thing for B, distance to the firm, to the frontier divided by distance to the firm is also 3 by 3. When you do for C, is distance to the frontier, which is 5, divided by distance to the firm, which is also 5. So you get 5 over 5. When you do for D, is distance to the frontier, which is 8, divided by distance to the firm, which is also 8. So that will be 8 over 8. So you can see that DMU, this DMU, D, it is efficient with efficiency score of 1. But it has been dominated by C because you can see that C is using less of input X1 compared to D. Okay. So it means that D is efficient in the Farrell sense, but it's weakly efficient. And so in Pareto-Koopman sense, D is exhibiting some slack. And the distance of the slack is 8 minus the 5, and that is 3. So if you are to use a slack-based measure, okay, the slack-based measure will punish D for where it is, and it will give it a lower score than what it will call it inefficient actually, instead of the Farrell efficiency. All right. So before we go into the R computation, I want to ask you to tell me, and you can raise your hand and tell me, you can unmute yourself and raise your hand and tell me. I just want you to tell me some few questions I'm about to ask here. Which DMUs are technically efficient? If you don't raise your hand, I'll call you. Which DMUs are technically efficient? Technical efficiency. Richmond.
DMU A0.
You forget about the 0 and move on.
A, B, C, and D.
Good. Which of them is technically inefficient? Salina.
That E.
Okay, very good. Now, which DMU or DMUs is mixed inefficient? Which DMU or DMUs is mixed inefficient? McClare.
We said DMU A and D.
Again?
A and D.
Perfect. Excellent. Well done. Why?
So because they are exhibiting slacks, they are on the side of the monotonicity.
Because they have slacks.
Yeah.
They have slacks. That is why. Okay. Now, who are the peers? Who do you think is a peer for DMU-B? This one is thinking. Software is going to determine all this, but I want to see your theoretical minds. Okay. Which firm is a peer for DMU-B? Stephen Morrison.
Please, B is a peer on itself.
What about C, Stephen Morrison?
C is also a peer on itself, please.
Okay. Now, Richmond, your hand is up. I want to believe that you had answers today. Which DMU is a peer for A? Which DMU is a peer for A?
D.
Please raise your hand. I want to be sure that I'm working with it. Which DMU is a peer for A? Anybody?
DMU-B.
Okay, Richmond, you're not used to raising your hands, eh? All right, so that is DMU B. Okay. And the B is in the closest neighborhood for A. Okay. And why is A not its own peer? You can tell me. Why is A not its own peer? Stephen.
Doc, it's because A is operating on the monotonicity line and exhibiting slacks.
A is simply exhibiting slacks. Fantastic. Okay. A is exhibiting slacks. You can say free disposable lines. A is exhibiting slack. All right. Now, which DMU is the peer or peers for D? Which DMU or DMUs is a peer for D for dog? Which DMU? Marclay.
DMU C.
What about E? Marclay, what about E?
Yeah, but E is inefficient.
Which peer is the peer for DMU E?
DMU E is either DMU C and D.
Which peer do you think is the peer for DMU E?
DMU D. I
can't hear you well at all.
DMU D and C.
How can D be a peer? D cannot be a peer. Who can tell him why D can never be a peer?
Because it's exhibiting slacks.
So why are you saying that it should be a peer for somebody when it is not even a peer for itself?
Yes.
Marclay, you are doing lottery. You are doing lotto. It can never be C and D because D was never using itself even as a peer. And because it's not using itself as a peer, how can it be a peer even for somebody? The person will ask, are you even a peer for yourself? A peer is a role model. And so the only peer for DMU E is C. That's the only peer. The only one. Okay, so understand and know the peers. Now let's go to benchmark. What point is the benchmark for B? What are the benchmarks? The benchmark is like the target. The targets. Which coordinates are the target for DMUB? Who can tell me? For DMUB, what is going to be the target for DMUB? I'm just trying to identify it here. What is the target for DMUB? Where I've indicated. What are the targets for DMUB? What are the targets? Stephen Kwashi.
No, DMUB it is its own target.
So what are the targets? When I say the target, I want you to tell me the coordinates of the inputs. What are the targets?
So 3, 3, 3. That's input.
3, 3. That's all.
X, yeah, X, yeah, okay.
What are the targets for DMU E? E. What are the targets for DME? Marclay?
DMC. That
So
is
what are the
5
times?
2. 5 2.
5 2. Okay. 5 2. So you need to understand it. These things, keep them in your mind because they are going to be revealed by the software. Once you understand it like this, now when you see it in the software, you understand it as well. Okay. We are going to calculate the technical efficiency scores for each one of them, the scale and all of this. All right. Any question? Any question? All right.